Give us just 1 second and we'll see if we can get this to work. All right, Lisa, can you give us a test for your audio?
Can you hear me?
So I can hear you. Do we know if the audio from the HDMI is being output as well?
None of you hear me?
I can hear you on, Lisa, I can hear you on my computer. Wait, maybe that's
You're going
because
to use this
I have...
jack as well.
Ah, brilliant, thank you.
And then on Skype, not on Skype, on Zoom, if you have the
Yeah.
okay, try that now, Lisa.
All right, Lisa, go ahead.
Can you all hear me?
Yes.
Okay. Should I start then or?
Yeah, so you go ahead. I'll be here for damage control with the HDMI.
Okay, if it ever stops working, I can't actually see what's on your screen, so just let me know and I'll stop. Okay, so hi everyone, good morning. My name is Lisa Kobayashi Frisk. I'm a PhD student at ICFO, the Institute of Photonic Sciences, and I'm working in the medical optics group led by Professor Turgut Durduran. And today I'll be talking about optical non-invasive measurements of microvascular blood flow. So the three main aims of this talk are firstly to understand the basic principles of diffuse optical measurements of blood flow. Secondly, to be able to identify and solve data quality issues from raw data. And finally, to be able to make informed decisions in data analysis to optimize data quality. So the main technique that I'll be talking about is called diffuse correlation spectroscopy, or DCS. So this is a non-invasive optical method to measure the microvascular and therefore local blood flow. The raw signal that we acquire, we call it G2, but that's the intensity autocorrelation of speckles. But what we actually use in order to retrieve the blood flow information is G1, or the electric field autocorrelation of speckles. G1 and G2 are related to each other through a very simple relation called the Siegert relation, and that's what's written at the very bottom of this slide here, and you can see that it's simple and that it also depends on this factor beta. So I'll explain what G1, G2, and beta are throughout this talk. So let's take a look at a cartoon of a DCS system. So at first glance, it's identical to a simple NIR setup. So you have a source fiber where you're injecting a coherent light source onto your tissue of interest. And then you have a detector fiber that detects the diffuse light a certain distance away from the source. So the photons coming from the source also experience absorption and scattering events, just like in NIRS. But what we're interested in DCS is the fact that these scatterers, so the main scatterer in biological tissue are the red blood cells, these scatterers actually move with time. And what that means is that the photon path length is actually changing slightly with the movement of the scatterers. Now, when the photon path length changes, what that means is that at the detector, you're going to see constructive and deconstructive interference, which translates to bright and light spots at the detector. And these bright and light spots, they're called speckles. So we call this a speckle pattern. So if you were to monitor one of these spots through time during your measurement, what you would see is that due to the fact that your scatterers are moving, this speckle pattern, its intensity will fluctuate with time. So if you were to just concentrate on one speckle, so one of these points of light intensity, and calculate how it is correlated, how its intensity is correlated to itself, then you can calculate the intensity autocorrelation curve of this speckle pattern. So that's the raw signal that we're acquiring with DCS. So this is the basic pipeline of the DCS system. We have a continuous wave laser. Typically, we use 785 nanometers, and it must be a long coherence length laser. We detect the diffuse photons using single photon detectors, and then we use correlators in order to be able to calculate these correlation curves. Then these correlation curves contain all the information that we need in order to be able to retrieve what we call a blood flow index, which is basically related to how quickly the intensity and electric field autocorrelation curves are decaying. So for a diffuse infinite medium, the electric autocorrelation, or G1, is given by this equation that's highlighted in bold font here. And we see that it's an equation that consists of two different exponential terms. And it also depends on a variety of different parameters, such as the optical properties of the tissue, the absorption and scattering coefficients, the wavelength of light that's used, etc. But the blood flow information is encapsulated within the term K, and I've highlighted the term that is related to the blood flow in red. And we call this term the blood flow index, so BFI, but since it's also been found to match the model of Brownian diffusion, we also often refer to it as dB for the Brownian diffusion coefficient. So I might switch between calling blood flow as BFI or dB. To extract BFI or blood flow data from G1, which again is derived from G2 using the secret relation, we use minimization algorithms such as fmin search in MATLAB. So all we do is we take our raw data and we try to fit it by updating our blood flow parameters. The general trends in flow data for increasing source detector separation rho is that the autocorrelation curves will decay faster. They will also decay faster with increasing dB or BFI or blood flow data. So what is BFI compared to some more, let's say, standard techniques? DCS has been validated with techniques such as MRI and PET. So it's been seen that there's a significant correlation between the relative cerebral blood flow measured in MRI and DCS. It's also been validated with PET, comparing the regional cerebral blood flow and the absolute BFI measured in DCS, where it was found that there was a significant correlation between the two techniques. And in this example of the PET validation study, a calibration factor was also calculated in order to relate the absolute BFI values from DCS with regional cerebral blood flow measured by PET. So what does DCS look like today? So today we are able to measure fast pulsatile blood flow signals using systems that have acquisition rates of around 40 Hertz. And these pulsatile signals have allowed us to introduce various blood flow derived parameters similar to what's been seen in the transcranial Doppler world. So for example, we measure pulsatility, which is the pulse height, so the difference in the blood flow index between the systolic peaks and the diastolic dips. We can also derive different parameters such as the critical closing pressure or CRCP. So DCS is quite powerful. If we combine DCS with different other monitoring systems such as physiological monitoring and NIRS, then we can measure a lot more than just blood flow. We can measure, as I said, the critical closing pressure. We can measure autoregulation, including cerebral autoregulation. We can measure misery perfusion, and we can also measure the cerebral metabolic rate of oxygen. So throughout this talk, I'll be referring to a data set that I took from an arm cuff occlusion protocol, and I included this data set just because it introduces really big changes in blood flow, and therefore I think it's a good example to show how DCS and the signal processing works. But obviously the same principles will apply for data taken in the brain. So the protocol looks something like this in this cartoon here. So we placed an arm cuff on the upper arm and then placed our optical probes located more distally from that arm cuff. For 3 minutes, we took a baseline measurement. So in this case, the arm cuff was not occluded, and therefore blood was able to flow normally into the distal region of the arm where we were looking optically. After 3 minutes, we occluded the cuff at 180 millimeter mercury in order to occlude the blood flow. And then we included a recovery period also of 3 minutes where then the arm cuff was released so that, again, the blood flow could be reintroduced to this distal region of the arm. If we look now at the raw data taken from this experiment, these are the G2 curves, so the intensity autocorrelation curves that were taken during this measurement. If we start on the left-hand side, all of the curves that are colored in red correspond to the curves that were taken during the baseline period. The blue curve corresponds to when the arm cuff occlusion started. And then all the brown curves show the curves that were acquired during the occlusion of the arm cuff. So what you see is that as soon as we started to occlude the cuff, all of these G2 curves started to shift towards higher values of the delay time tau. So they're decaying much more slowly as the blood flow was stopped. On the right-hand side, we see then the recovery period. So the red curve shows the moment at which the arm cuff was released, we saw then that there was a drastic change in the G2 curves where they all started to decay a lot faster. So the green curve shows this hyperemic peak, and then the rest of the curve shows just the behavior of G2 during the recovery period. Now using, in this case, I used fmin search in MATLAB in order to derive the dB values, so blood flow values. So we can see that during the baseline period, that's what's shown between the first two vertical lines. So when the G2 curves were all quite stable, we also have similarly stable values in dB. As soon as we occluded the cup, we see this drastic drop in dB, which was related to this slower decay in G2. As soon as then we released the cup, we see this drastic increase in dB. That was the hyperemic peak that's circled in green and corresponds to the green curve shown here. And then just during the recovery period, we see that they all kind of slowly become more stable and they have around the same decay rate in G2. So from here on out, I'm going to be talking about the raw data, how to assess the raw data quality, first by looking at just the G2 shapes, then looking at the beta factor, and also talking about the detected intensity levels. Then I'll touch on the analysis methods, so how to fit these curves, what to think about when doing the curve fitting, and also talk a little bit about using multi-layer models. I'll talk about additional considerations to increase precision and accuracy in DCS measurements, as well as then finally talk about different speckle-related techniques to measure blood flow. So this is just an image, so you have an idea of what a DCS system looks like. On the left-hand side, you see a device that we built in the lab. It consists of 16 detector channels. So this all fits within a standard 19-inch rack. It's not very big. Most of the systems are handmade lab systems, but also a few commercial products also exist. So talking about the raw data, so as I hope you know by now, the raw data are these G2 intensity autocorrelation curves. And just the shape of this curve gives us a lot of information about how good our data is. So first off, we can see that this curve starts at around 1.5. The point at which this curve starts is related to this beta parameter that I talked about when introducing the Siegert relation. And beta is normally calculated as the average of the first 3 points on the G2 curve. And then the second point to look out for when looking at these G2 curves is just to look that they have this clean decay following the double exponential form of G2. So let's look a little bit more in detail in beta. So what is this beta factor? A beta is a system-based parameter, and it depends on the coherence of the light source that you use, the polarization of that source, as well as the detection optics. So in a typical DCS system, we use unpolarized light and single-mode fibers to detect the speckles, which results in a beta of 0.5. That's the typical value, which means that your G2 curve should start around 1.5. However, in one experiment, as an example, we saw that we had, for example, a beta of around 0.35. And possible reasons for that happening can be that you have external light accidentally entering your detector fiber, in which case you can try to cover your probes better. You might also be seeing some light channeling, in which case you want to try to get better probe contact with the skin. The next point to look out for in these G2 curve shapes was to look at the decay in the tail. So you want to make sure that it decays properly following a double exponential form. The black curve that I include in this figure here clearly deviates from that form. Possible reasons, it's mainly due to bad probe attachment. So it's important to monitor these G2 curves during measurements so that you can quickly pick up on if your probe has detached or not. For example, this is our same arm cuff measurement data, and if you look here on the right-hand side, you see this bad curve that clearly isn't decaying properly. So this is just visually, it's a bad curve. I wouldn't try to fit it, and I would remove it during post-processing. And if you see that something like this happens during your measurement and it stays constant during a long time, try to get your probe to attach better, see if it came off and see if you can attach it better. So another important thing to talk about is these G2 shapes might also give you some idea about whether you're actually looking in a diffuse regime or not. So in this example here, my colleague was studying a patient who had had a malignant stroke and a craniotomy. And what she saw was that her recorded G1 curve, that's the yellow curve here, looked very strange. And so she actually couldn't even fit and recover a blood flow value in this case. And when looking at the CT image of this patient, it's likely that the photons were probably not diffuse enough and that brain was probably not reached. And this was probably due to just the pathology, the severe pathology of this patient. That's a pretty extreme case. Another measurement on, again, a patient with a craniotomy and a swollen muscle. In this case, a pretty decent looking G1 or G2 curve was obtained and the data could be fit. However, looking at the CT image after processing this data, it revealed that probably the location of the probe indicates that she was probably not probing brain tissue and was rather just imaging the swollen muscle tissue that was located above the skull. So since we're using diffuse optics, we are never truly sure where we placed our probes. If you're measuring a patient with severe pathology, like in these cases, it is worthwhile to check where you've actually placed the probes and make sure that you're probably probing brain tissue with a higher probability. The last thing I want to talk about in regards to raw data is just talking about your detected intensity levels. So in this case, this was data that was taken continuously. In the top row, I show the detected photon count rates in kilohertz. In the middle row, I show the fitted blood flow values. And in the last row, I show the raw G2 data. And what you'll observe in the top row is that the count rate decreased a lot during this measurement. So it started from around 30 kilohertz and then dropped down to around 5 kilohertz. And you can see how that affected the dB values. So when we had a good high count rate, we saw that the dB values were quite constant and they were measured with a rather small coefficient of variation. However, as the count rate decreased, we can see that our dB values are all over the place. And it's also kind of reflected in our G2 curve. So the G2 curve, when the count rate was high, is obviously a lot cleaner and smoother than our G2 curve that was measured when the count rate was very low. So it's also good to keep an eye out on your detected intensity levels. Possible reasons for why you can see this kind of decrease in your intensity might again be the fact that you have attached your probe badly. Depending on the protocol, you might also be introducing large changes in the optical properties of the tissue. So these things could happen. So I've repeated probe attachment 3 times now. It's important to have your probe attached well, both for being able to have accurate betas in order to have a good decay, so your overall shape in G2, as well as to make sure that you're getting a good detected intensity level. So in our case, we don't have fancy headgears, but we just use a combination of lots of tape and bandages to keep our probes in place. Now I want to talk about the data analysis. So once you've taken your raw data and you've looked at it and you're happy with the quality visually, it's time to analyze your data. So we're doing this by curve fitting, as I said. However, when fitting your data, it's important to consider which part of your autocorrelation curves you are fitting. So it's been shown that if you fit the entire curve, so fitting even the longer delay times, you're going to be less sensitive to the brain. So when doing brain studies, it's important to cut off your G1 curves and then just fit the earlier delay times. So that's the case shown in cyan here. And again, just like in NIRS, use longer source detector separations in order to increase your sensitivity to brain tissue. Here I just show an example. This is data taken from the brain. In the blue lines show the dB values that were obtained when fitting the data by cutting the data for G1, only including G1 greater than 0.7. And the red lines show the corresponding fits for dB when fitting for the entire curve. You can see how the absolute values are are different, both how the blue and the red lines are different from each other on the left-hand side, and also how the relative cerebral blood flow changes relative to this baseline position, how they also change depending on how you decide to fit the curves. Again, the same principles apply in the arm as well, since it's also kind of a layered medium. We also see that the optical properties that you choose when fitting the curves are also important. If you remember, G1 and G2 are dependent on the optical properties. So here on the left-hand side, on the top left, we see how the absolute blood flow values change when changing the reduced scattering coefficient, keeping the absorption coefficient constant. The one right below it is again the same. In this case, I kept the reduced scattering coefficient constant and changed the absorption coefficient. And so we can see how the absolute flow changes differ greatly depending on the absorption and reduced scattering coefficients that you choose to use for fitting. On the right-hand side, I showed the relative blood flow changes for, again, keeping mu A constant on the top and changing mu S prime. We can see that the relative values are not affected. And then the same thing on the bottom, we see keeping mu S prime constant and changing mu A. Again, the relative changes are not affected by your optical properties. So if you're interested in absolute measurements of blood flow, it's very important that you have accurate measurements of optical properties. Okay, the next thing I want to talk about is what kind of model that you want to use. The G1, the equation for G1 that I showed earlier was for a homogeneous semi-infinite medium, which is obviously a big simplification of the physical reality. So obviously our head is not a homogeneous semi-infinite medium. There are articles out there that have corrected this for layered structures of the head. In the first case, a simple correction factor was applied in order to account for reduction in the measured blood flow due to partial volume effects. And then there have also been lots of different models, multi-layered models that take into account the influence of layered mediums such as the head. We look at one of these studies that used a two-layer model. So in this case, the two-layer model consisted of an outer scalp and skull layer, and then the second inner brain layer. So what was done here was the blood flow differences between normal and hypocapnia in pigs was studied using computed tomography perfusion as well as DCS. In the first two bars here, we see the cerebral blood flow that was measured by computed tomography perfusion, where it was seen that there was a significant difference in blood flow in the brain between normal capnia and hypocapnia. In the next two bars here, we see the BFI measured by DCS in the second brain layer, where again, the results are similar. So there was a significant difference between normal capnia and hypocapnia. The next bars show the scalp flow that was measured by CTP, where in this case, there was no difference between normal capnia and hypocapnia. Similarly, no difference was seen in the BFI measured by DCS in the scalp and skull layer. So, which shows that the two-layer model agreed very well with the computed tomography perfusion values. However, looking at just using a homogeneous model, so this simple model that I was talking about earlier, and DCS measured at both 2 centimeters and 2.7 centimeters, this significant difference between blood flow in normal capnia and hypocapnia was detected. So the reason why I wanted to bring up this study was to show that multi-layer models are better descriptions of reality, but they're not always necessary. And the reason for why why you might want to use a homogeneous model is that it's a simpler model, which means that it's more simple to implement, and it doesn't require the a priori knowledge of optical properties of each layer and the layer thickness that is required when applying these multi-layer models. So 2-layer models have been done. 3-layer models also exist where the scalp and the skull are differentiated. And I just included the discussion from this article here, where it was seen that the semi-infinite homogeneous model is actually accurate in the regime where the scalp blood flow changes are similar to the brain blood flow changes. So we have these multi-layer models. However, in all of these models, you need to know what is the optical property in each of your layers and how thick each of your layers are, which means that they are a little bit more complicated to implement. And in a lot of cases, actually, your semi-infinite homogeneous model is going to be able to detect the changes within the brain. So now I want to talk about how to improve your accuracy and precision in DCS measurements. So accuracy in your blood flow values derived by DCS are affected by the extracerebral contamination as well as the modeling accuracies, as I just discussed. In order to increase the accuracy considering these two factors, well, one is, as I said, you could try to apply a multi-layer model, but there's also been other kind of more work done in order to try to extract the extracerebral contamination in DCS data, including, for example, a pressure modulation algorithm. In order to increase the precision in DCS measurements, so precision is affected by the detected count rate. The greater detected count rate you have, the better your precision will be, and also the number of your detector channels. So the greater number of detector channels that you have, again, you're going to have a greater precision. So possible solutions in order to increase your precision in BFI or blood flow data is you're going to want to increase both of these factors. So in order to increase the detected count rate, you can think about changing your probe design. So you can have, for example, these dual source probe designs, in which case that's this image shown here on the right-hand side, where the two red dots are representing the source fibers that are located equidistant away from a detector fiber. And in this way, you can inject in total more light onto the tissue without exceeding laser safety limits. If you're working well below the laser safety limit, you can also do the simple solution, which is to simply increase your source power. And also, there's a lot of talk about going and using longer wavelengths rather than 785 nanometers in order to increase the detected count rate. Increasing the number of detector channels was the second point. There's really only one way to fix that, is to increase the number of detector channels. The drawbacks in all of these solutions is that increasing the source power is often impossible to do because we are limited by laser safety limits. Using longer wavelengths, especially 1024 nanometers, requires specialized detectors. So in practice, it's much more difficult to implement. Increasing number of detector channels, while it seems like a simple solution, will result in a much more expensive device as well as much larger. And I also want to just include this slide here to say that the data quality in DCS is affected by similar things as NIRS. So motion does affect us. Ambient light is an issue. And the contact of the probe to your skin is also an issue. In order to monitor all of this, we have integrated different sensors onto our optical probes so that we can monitor, for example, motion artifacts using an accelerometer, etc. This image here is just showing that integrated probe with lots of sensors with the optical fibers. This probe was made for the VAS-COVID project. However, it's not necessary. This is an ongoing EU project, VAS-COVID, but it's not brand new, this idea. It has also been implemented before in other European projects, such as the Baby Looks project. So I've been talking now about standard DCS. However, a lot of other speckle-based techniques do exist, so I think I should talk about those as well. So we have time domain DCS, which uses a pulsed light source and time-gated detection, which allows us to discriminate better between the upper and lower layers, which means that we have better brain sensitivity. And then more recently, there's also been publications on interferometric DCS or IDCS, where heterodyne detection technique is used. And this allows for a better detected signal to noise, as well as the possibility to time gate the detected signal, which means that also, just like with time domain DCS, there will be an increased brain sensitivity. Then there's a whole host of other techniques that don't measure G1 and G2 curves. So they don't directly measure the intensity autocorrelation of speckles. And so I've grouped them into a different subcategory, and I call them speckle contrast-based techniques. And there's lots of different names for these techniques, different abbreviations, but I'm going to be focusing and calling them speckle contrast optical spectroscopy, or SCOS, as well as speckle contrast optical tomography, or SCOT. So these speckle contrast-based techniques measure what we call speckle contrast, and it's abbreviated as kappa. I also often refer to it as kappa squared, and the reason for that is because the kappa squared is directly related to G1 squared, so the electric field autocorrelation of speckles that we're used to now from the DCS, through this equation here. So it's related by this integral over the delay times from the limits of 0 to t, where this big letter T is the exposure time of the camera you use. So speckle contrast is measured by using two-dimensional detector arrays, and therefore cameras. And what we do is we take images of our diffuse speckle pattern, and then we choose an ROI on our image. And from there, we build a histogram of the speckle intensities. So kappa squared, it's related to G1 squared through this integral, but what it actually is that it is the ratio between the standard deviation in intensity and the mean intensity, all squared, in the case of kappa squared. So it's actually a really simple measurement. All you need to know is you need to know the histogram of your speckle intensities. And the big advantage to these speckle contrast-based techniques is that you have a much cheaper cost per detector channel compared to DCS. Because if you remember, one of the ways to increase the precision in your DCS measurements was to increase the number of detector channels. And I said that there is a drawback to that because of the high price, as well as increasing the size of your system. But since in speckle contrast systems, we are interested in using detector arrays, so cameras, each pixel in your camera is actually a detector channel. And since we have megapixel cameras, it means that we have lots and lots of detector channels for a much smaller price per detector channel. So here I'm just showing an example from a study on functional SCOT that was done in mice. So in this case, the cerebral blood flow response to pulse simulation in mice were recorded using both SCOT, speckle contrast optical tomography, as well as MRI. And it was found here in this top, the subplots A and B, there was a good spatial agreement between SCOT and MRI. And also there was shown to be a clear CDF response to the 4-pulse simulation measured by SCOT compared to a sham measurement. So speckle contrast techniques are simple. They are just measuring a histogram of speckle intensity. You have access to lots and lots of detector channels. However, there are challenges involved in these techniques as well. So the big challenge in speckle contrast techniques is to get a good signal. Since we're measuring just the histogram of speckle intensity, what happens is that our detector cameras have associated noise with them, and this noise also has an associated probability distribution, and that will affect therefore your measured speckle contrast values. So cameras typically they all have shot noise, and they also have associated dark and readout noise, which all have their own distribution profiles. What that means is that if your signal is overwhelmed by your noise, you're no longer going to be able to accurately distinguish your standard deviation speckle intensity nor your mean value in speckle intensity, which means that your kappa squared is affected. And typically what we see then is that in the regime of lower detected photons, so at longer source detector separations or very short exposure times, we see that our kappa squared values deviate normally with a big increase in these regimes. Since I talked about precision and accuracy in DCS, I also wanted to talk about it for speckle contrast techniques. So the precision in speckle contrast is greatly affected by the number of speckles that you use in order to calculate your speckle contrast, kappa squared. So the more number of speckles that you include in your calculation of kappa squared, the greater precision that you can have in kappa squared. And for the accuracy in kappa squared, you will have a greater accuracy in kappa squared with an increase in the number of your incident photons. So although there are challenges associated with SCOS, I think it's still very promising. Several groups are working in miniaturizing and fiber coupling SCOS devices. So far, SCOS and SCOT have basically always been done in free space optics setups. However, by fiber coupling these systems, we're going to be able to measure patients in motion. And also lots of groups are playing with the idea of using multimode fibers for detecting speckle contrast signals. And this is a big advancement because it will increase the detected signals. And the reason why I think SCOS is really nice is because the devices can become much smaller than DCS systems and also much cheaper. And does that mean that maybe we'll finally be on the road to having a fully wearable and non-invasive measurements of blood flow? So in this picture here, you can see the device of my colleague. This is the detector in SCOS, but it's fiber coupled and it just fits right on the palm of his hand. We also have an NIH project between ICFO and the Washington University in St. Louis to develop a high-density SCOT system. So just taking advantage of the fact that of the power of speckle contrast measurements, could we develop a high-density SCOT imaging system that would not be prohibitively expensive? So the main aims of this talk were firstly to understand the physics behind the signal in diffuse correlation spectroscopy and how moving scatterers result in speckles with fluctuating intensity. So I hope that that has been covered. In the second aim, I hope that I have been able to talk about when acquiring blood flow data using DCS, that it's important to keep an eye out for the shapes in the intensity autocorrelation, G2, the values of beta, as well as the total detected intensity. And finally, to be able to take care when analyzing data, the extra cerebral effects, such as the cutoff in G2 for fitting and the choice of optical properties. And just to finish off, diffuse correlation spectroscopy is a method for measuring potentially pulsatile blood flow signals non-invasively in the body. There are other related techniques such as speckle contrast techniques that can also measure blood flow non-invasively in the body. These techniques are all related to near-infrared spectroscopy, and therefore they all suffer from the potential extracerebral contamination. And then there's also issues related to the presence of motion artifacts. Low detected photons can also be an issue. However, there are strategies to reduce these effects. And finally, just that emerging methods will allow for even better depth sensitivity using time resolved systems such as time domain DCS and interferometric DCS, and better signal quality and smaller, more wearable devices are also being developed through different speckle contrast optical systems. So hopefully in the future, we will have a fully wearable blood flow monitoring device. That's it from me. So thank you for listening, and thank you to all the funders and all my colleagues in the medical optics group at ICFO.
Wonderful. Thank you so much, Lisa. We got through it. The HDMI cable did.
I did.